Thanks, Arun. Thanks, CII and WRI-India for giving an opportunity for sharing our experience of what we have done in our dye house. This is just a brief intro about our dye house. We have about a capacity of 6,500 kgs per day of dyeing knitted fabric, and we are in operation for last 13 years, and we fall under the MSME small category. And our dye house is located in a industrial estate which is supported by the Tamil Nadu state government. Varun, can I take control of the screen? It's like a, is it so that I can move the slides by myself?
You have control, Mr. Manoharan. Please go ahead.
Okay, right. Thank you. Because I'm not able to move to the next slide. Can you just switch down?
You can just use your arrow keys or click on the screen. You should be able to move.
Oh, I click on the screen. Okay. Okay. As I am coming from a textile industry, or basically the fashion industry, in the entire textile supply chain, without textile dyeing, there is no value addition. Otherwise, you will be seeing plain, because natural cotton is dull yellow in color. But if you see any thing which we wear, starting from myself to yourself and all around you, everything is in different colors because of the textile dyeing. But there are two major issues which we see in the textile dyeing. One is which is promoted very heavily even today in social media, etc., is high water consumption. So in the textile dyeing part, and which is resulting in high effluent generation, and there is a high energy consumption that is involved in the production process. So how are we handling it? So as far as the effluent is concerned, our factory comes under a zero liquid discharge scheme. That means we don't discharge any liquid effluent, not in a single drop of liquid effluent, neither inside the factory nor outside the factory into any river body or etc. The entire effluent that is generated is treated, recovered, and reused. So in the recovery process, we get about 90% of recovery, 10% is lost due to natural evaporation, etc. So our freshwater requirement has come down by 90%. So we use only 10% of fresh water for our production top up. So remaining 90% is from the effluent that is generated. So this takes care of both the issues: one, handling of the effluent, and the handling of the freshwater requirement. So coming to this sessions, that is the energy efficiency. Textile dyeing requires a lot of huge energy consumption, both in terms of thermal energy and electrical energy. So my presentation here is to focus on the thermal energy. The textile dyeing happens in a different, it is not a single process. It takes in maybe about 8 steps to 14 steps, depending on the color, depending on the fabric you want to dye, etc. So in our dyeing process, typically we heat the fresh water that comes in, maybe at 30° centigrade, to temperature varying from 60° all the way up to 120°, depending on which fabric. For example, polyester we do dyeing at 120°, and normal cotton we do at 80, 85. So basically our heating range is from 30° fresh water all the way up to 60° to 120°. And once our dyeing process is over, we cool them down to 80°, between 60 to 80°, and drain the water. So the hot effluent, takes away the heat energy along with it. So we planned on implementing a heat recovery system, so which will help in both these aspects. So what we have done is we like to recover the waste heat from 3 different sources. As I said, the wastewater or the textile effluent which is being drained from the machine is being let out anywhere between 60 to 80°. So we like to recover the heat from there. And also I showed you that we heat all the way up to 120°, but we don't drain like that because that will affect the fabric. So we always cool from, say, 120° to 80°, and then we drain it. So the cooling, we give it is basically a shell and tube heat exchanger, where we send a fresh water at 30° and cool the dye bath which is at 120°. So we like to recover the heat from that cooling process also. and the third is from the boiler. Whatever the flue gas thermal loss or whatever the waste heat that is being sent out through the flue gas, we wanted to recover. So these three aspects has been integrated and put it into a single solution. So this is kind of a pictorial representation. I think it will look a little bit complicated, but it is basically the three things. If you can see here, my dyeing machine. So whatever the cooling return, using a plate heat exchanger, we are recovering the heat. So the next one is the effluent that is being drained. So we collect it and then we again through a plate heat exchanger, we recover that heat. And third economizer is at the boiler level, where at the stack at the chimney, before it goes into the chimney, we recover the heat from the flue gas. So all these waste heat or which was getting lost previously are all collected into a single tank, which is about 200 KL, and we use that hot water for our production. So this entire system was designed by Bosch and designed, implemented by them. So this gives a picture of what is there physically at my factory. The one on the right side is the 200 KL tank. So the middle portion will have 60-degree hot water, and the top one will have the 80-degree. And the pictures on the left side shows you the various plate heat exchangers we have put in to recover the heat from both hot effluent and also from the cooling return process. So this is actual data which we have taken once the COVID pandemic kind of lockdown was released, and when we started our production, and we wanted to test how much savings we were getting with this implementation and without implementation. What we have done is like we did an alternate week test. So 1 week, because typically our dye houses runs from Monday to Saturday. So we took that as one production, and because in the weekends we do the boiler cleaning. So we took, we ran the system or the production with Bosch implemented weight heat recovery. The next week we switched off the Bosch system. The third week again we ran it, and fourth week we again switched off just to see how the variation is. So our savings was ranging from 22.7% to 26.5%, because our production is not standard, because depending on what our customer requires, we will be dealing with different fabrics, different colors. So the kind of production which we do in week 1 may not be exactly matching with week 2 or week 3. So we are taking an average across 4 weeks. So on an average, we were able to see there was a 24% reduction in the fuel, which is specifically consumed at the production level. So I had 2 boilers. The first row shows the steam production at combination of those 2 boilers, 310 boiler and 210 boiler. And the second one shows me the total wood consumption in those 2 boilers. The third row shows the specific fuel consumption. And fourth row is the steam consumed for processing, because the steam that is generated from these 2 boilers are used in 2 categories. One is at the production house, and the second one is for the zero liquid discharge scheme at our ETP. So here we focus only on the production. So the fourth row is out of the total steam produced, that is shown in the fourth row or first row. The fourth row shows how much is consumed for the production, which is roughly about 1/3. And using the specific fuel consumption, we theoretically consumed how much wood is consumed for production, and what is the amount of fabric processed in that week, and we finally arrived at the wood consumed per kg of fabric. So with Bosch system, we were using about 1.05 kg of firewood for every kg of fabric we dyed. Without Bosch system, it was 1.362 all the way up to 1.39. So this is our practical data which we used, and we have repeated the study even last month also. The results were more or less the same. So when we go into the economics, so average wood consumption for processing area alone was about 7,000 kgs per day, and we were looking at a fuel savings based on our practical measurements is 24%. So Wood savings per day is 1680 kgs, and our purchase cost of firewood is about an average is 4.9 rupees per kg of firewood. So per day we are saving about 8,200 rupees. Conservatively, I have shown you we are operating only 290 days in a year, so about 24 lakhs is the annual savings. And total investment for this entire waste heat recovery from three sources. One is the effluent, cooling return, and flue gas is 85 lakhs. So the return of investment calculation is 3.5 years. This is on a theoretical basis, but what we have done as an agreement with Bosch is like instead of giving all the savings as a repayment, we have structured our finance such way that 70% of the savings goes towards the repayment of the capital investment and the interest, and 30% is to improve our own cash flow, because we need to have some better cash flow because of these savings. So we have structured our finance over a 5-year period. So within 5-year period, I will be repaying the capital, I will be repaying the interest. At the same time, for 5 years, I will be getting 30% of the savings as a positive cash flow into my system. So from the 5th year or whatever the savings that comes, it is 100% it will to our bottom line. And if you can see this, as I said, my turnover is about 25 crores, 23 to 25 crores per annum. So this 24 lakhs is direct 1% improvement in my bottom line. So which is very significant savings.
Mr. Suresh, we'll request you to conclude in next 2 minutes, sir.
Yeah. So our what we have seen is the benefits is we have seen a 24% result reduction in the steam consumption, but we had other benefits like a low temperature going into the effluent helps us to save the treatment cost over there, and because of hot water ready at the machine, our peak load from the boiler is reduced, so which further enhance the boiler performance. Out of 2 boilers, we have even moved 1 2-ton boiler into a standby mode. So only 3-ton boiler we are using. These are the benefits we have seen. So we have done various aspects. So we are in the process of getting the. We have initiated it. So we are going for the CII GreenCO certification, and I have just 2 more slides. I'm going to repeat what Akshay said from a practical point of view. There are 2 things for in a MSME which I see around the colleagues or other investors in my area is people are not investing in utility monitoring equipment. So whatever savings I am saying, which is all based on real-time data, is because we have equipments to measure it, like the steam flow meters. They have used 5 steam flow meters to find out exactly what is the steam generated in each place and how much is utilized in different places. What are the weighing scales, energy meters? Because even people like when CII GreenCO team comes, if an unit doesn't have a steam flow meter or a weighing scale, even to find out a boiler efficiency that is happening right now is very difficult. So they can't help you to improve it. So please invest in energy monitoring equipment. And the next one, and the last slide is, please invest in IoT. So because all these energy equipments, like whether it could be energy meter or a steam flow meter or running hour meter, nothing can be manually maintained. You can't ask your person to record a reading every 1 hour. There is a fatigue sets in. They don't do it. So if you can see, we are from IDATEC software, we have installed an IoT based system which records everything on a minute by minute value. So you can put all these things in either vendor cloud or your own private cloud. So without an real-time data acquisition and analytics, you will not be able to pinpoint your return of investment. So these are my things for the MSME industries who are listening to it. Please invest on equipments. Please invest on IoT-based monitoring systems or real-time data acquisition and analytics. So with this, I conclude my presentation. Thanks, CII and WRI once again.